Hello students, welcome back to Learn 24. In this video, we are going to cover an important topic called colligative properties. Now, in order to get a solution, I have to mix solute with a solvent, right? Yes. Now, I don't want to know any information about the nature or the characteristic of this solute that I have added. Only thing I want to know is the amount of solute that I have added. That is called the colligative properties. Colligative properties only depends on the number of particles of solute, not on its nature. It depends only on the number of particles of solute, not on the nature. As you can see, the colligative properties are of 4 types: relative lowering of vapor pressure, then comes the elevation of boiling point, then depression of freezing point, and the last one, osmotic pressure. Let's study one by one. First one is the relative lowering of vapor pressure. As I told you earlier, when I add a non-volatile solute to a volatile solvent, the vapor pressure of solution just decreases when compared to the pure solvent. When I add a non-volatile solid to a volatile liquid, the vapor pressure just decreases. The vapor pressure just decreases. PA will be less than PA0. What is PA and PA0? PA is the partial vapor pressure and PA is the vapor pressure of pure solvent. Now, P is equal to PA. The total vapor pressure is only contributed by the volatile solvent. That is the partial vapor pressure of A. Then I can write P is equal to PA. As we know, PA is directly proportional to the mole fraction of A, right? In order to remove this proportionality sign, I have added a constant called PA0. Then I got an equation PA is equal to PA0 into mole fraction of A. In order to know how much vapor pressure has lowered, PA minus PA0 minus PA, I can get how much vapor pressure has lowered, that is delta PA. Now, we know the value of PA, right? PA is equal to PA0 into mole fraction of A. That I have substituted that in the place of the PA0 minus PA0 into mole fraction of A. In this equation, PA0 is common, right? So, I took PA0 outside. That PA0 into 1 minus mole fraction of A. I got the equation PA0 into 1 minus mole fraction of A. We know that mole fraction of A plus mole fraction of B is equal to 1. Then I can write mole fraction of B is equal to 1 minus mole fraction of A. I can substitute mole fraction of B instead of 1 minus mole fraction of A, right? Then I got an equation delta PA is equal to PA0 into mole fraction of B. In order to know the value of mole fraction of B, I can take this mole fraction of B into the left hand side. Then I can write mole fraction of B is equal to delta PA divided by PA0. As we know, delta PA is equal to PA0 minus PA. I just substituted that here. PA0 minus PA divided by PA0. This equation is called the relative lowering of vapor pressure. This equation is called relative lowering of vapor pressure. Now, I don't want to know about this equation. All I want to know is this: how much amount of solute that I have added. That is the colligative property, right? Now, I want to know the molar mass of solute. Molar mass of solute. In order to get that, let's continue the derivation. Now we know mole fraction of B is mole fraction of B is the number of moles of B divided by total number of moles of A and B. Mole fraction of B is equal to NB divided by Na plus NB. I just substituted here. Then I got an equation PA0 minus PA divided by PA0 is equal to NB divided by NA plus NB. When compared to NA, the NP is very less. So I can write NA plus NB is nearly equal to NA. NB is very small when compared to NA. So like I can write NA plus NB is nearly equal to NA. Then I can replace this as NA. Then I replaced this as NA. And I got an equation like this. Now NA and NB. Na is the given mass of A divided by molar mass of A. Given mass divided by molar mass. Similarly, NB is the given mass of B divided by molar mass of B. We got the values of Na and NB. Just substituting that and on cross multiplication, I will get W into Ma divided by MB into WA. W and WB is the given mass and Ma and NB are the molar mass of A and B respectively. Then I have to know the value of MB, that is the molar mass of solute, MB. Now in order to get that, I took this on the left hand side and the rest of the things on the right hand side. Then I will get an equation MB is equal to WB into MA into PA0 divided by WA PA0 minus PA. This is the equation to find out the molar mass of solute. By knowing all other terms, I can calculate the molar mass of solute. This is the colligative property. Moving on to the second colligative property, the elevation of boiling point. As we know, vapor pressure of solution is less than that of pure solvent, right? We already learned about that. But the boiling point of solution is greater than of the pure solvent. When I add solute, boiling point just increases. Now, what is the boiling point? Can you tell me what is the boiling point? Definitely yes. Boiling point is the temperature at which the vapor pressure of solution become equals to the atmospheric pressure. That is called the boiling point. When the vapor pressure of solution equals to the atmospheric pressure, that is 1 atm. 1 atm is the atmospheric pressure. When they equal to 1 atm, at that temperature is called the boiling point of that solution. Now, the boiling point of pure solvent is TB0 and boiling point of solution is TB. Let's indicate boiling point of pure solvent as TB0 and boiling point of solution as TB. Now, TB is greater than that of TB0, right? TB is greater than TB0. Now, to find out how much amount of a boiling point have increased, how much boiling point has increased, TB minus TB0. That is the elevation of boiling point. Delta TB is equal to TB minus TB0. Elevation of boiling point. How much boiling point have increased? Elevation of boiling point. Now, delta TB is directly proportional to the M. M is the molality or molar concentration of solute. Delta TB is directly proportional to M, molality. In order to remove this proportionality sign, I have added a constant called Kb. Kb is the ebullioscopic constant or boiling point elevation constant. Don't forget this term, ebullioscopic constant. Now, delta TB is equal to Kb into M. Delta TB is equal to Kb into M. Now, let me explain it with a graph. Now, I took vapor pressure on the y-axis and temperature on the x-axis. 1 atm is the atmospheric pressure. 1 atm is the atmospheric pressure. And I took solvent and solution. Let me take this as the room temperature. At room temperature, the solvent have the vapor pressure this much. And as temperature increases, the vapor pressure of solvent increases and reach at the atmospheric pressure, At that temperature is called the boiling point of the solvent. that temperature is the boiling point of solvent. When the vapor pressure of solvent equals to the atmospheric pressure, this temperature is the boiling point of solvent. We indicate that as TB0. Now, at room temperature, the vapor pressure of solution was this. As the temperature increases, vapor pressure also increases and reach at the point of 1 atm. And that temperature is called the boiling point of that solution. Boiling point of solution, we indicate that by TB. And the difference between TB0 and TB is delta TB. Clear with that? Delta TB is the difference between TB0 and TB. The boiling point just increase it. The solution having the higher boiling point than the solvent. Clear with this graph? Alright. Now let's move on. We have to find the molar mass of solute, right? In order to get that, let's continue the derivation. As we know, delta TB is equal to KB into M, right? M is the W2 divided by M2 whole divided by W1 divided by 1000, right? W2 and W1 is the mass of solvent and solute. Given mass of solvent and solute are the W1 and W2. Now, M2 is the molar mass of solute. We have to find out what is M2, right? It's the molar mass of solute. Now, on cross multiplication, I will get M is equal to 1000 into W2 divided by M2 into W1. I am just substituting this M in this place of here. So, I will get delta TB is equal to KB into 1000 into W2 divided by M2 into W1. I have to find out the molar mass of solute. In order to get that, I took M2 on the left hand side and rest of the thing on the right hand side. So, M2 is equal to KB into 1000 into W2 all divided by delta TB into W1. I got the equation for the molar mass of solute. By knowing all other terms, I can find out the molar mass of solute, how much amount of solute that I have added. Again, it's a colligative property. Now, next colligative property is the depression of freezing point. Now, the third colligative property is the depression of freezing point. Now, when I add a solute to the solvent, freezing point just decreases as like in vapor pressure. The freezing point of solution is less than that of the pure solvent. Freezing point of solution is less than that of pure solvent. Now, what is the freezing point? Freezing point is the temperature at which when a liquid becomes in its solid state, right? More correctly, I can say freezing point is the temperature at which the vapor pressure of liquid becomes equal to the vapor pressure of its own solid. Freezing point is the temperature at which the vapor pressure of liquid becomes equal to the vapor pressure of its own solid. It's called the freezing point. Now, let's indicate TF0 as the freezing point of pure solvent. Freezing point of pure solvent is TF0 and TF is the freezing point of solution. TF is the freezing point of solution. Now, TF is less than that of TF0. TF is less than that of TF0. Now, let me explain it with the help of graph. Now, this graph we already know that at a room temperature, the vapor pressure of solvent was this, and at 1 atm pressure, when it reached 1 atm pressure, that temperature is called the boiling point of that solvent and solution. We already know about that. Now, this is the vapor pressure of frozen solvent. Freezing point is the temperature at which the vapor pressure of solvent becomes equal to the vapor pressure of that solid, right? Now, this is the point where the vapor pressure of liquid solvent becomes equal to the vapor pressure of frozen solvent. So, this is the temperature of This is the freezing point of solvent. This is the freezing point of solvent, TF0. Freezing point of pure solvent, TF0. Now, this is the point where the vapor pressure of solution becomes equal to the vapor pressure of this frozen solvent. This is the freezing point of this solution, TF. This is the freezing point of solution, TF. Now, delta TF is the difference between these two. Delta TF is the difference between TF and TF0. In order to get how much freezing point has lowered, depression in freezing point, delta TF is equal to TF0 minus TF, depression of freezing point. Now, delta TF is directly proportional to molality. Delta TF is directly proportional to molality, as like in elevation of boiling point. Now, in order to remove this proportionality sign, I have added a constant called Kf. Constant called Kf. That is the freezing point depression constant or cryoscopic constant. Cryoscopic constant or freezing point depression constant. What does K be? Can you remember that? What does K be? Yes, it is the ebullioscopic constant and Kf is the cryoscopic constant. Now, I got an equation, delta TF is equal to Kf into M. Kf into M. In order to get the molar mass of solute, M, we already know the M is equal to 1000 into W2 divided by M2 into W1. W1 and W2 are the given mass of solvent and solute. M2 is the molar mass of solute. That is what we have to find out. And now, instead of M, I have substituted this equation. Delta TF is equal to Kf into M. Instead of M, I have substituted the equation and I got delta TF is equal to Kf into 1000 into W2 divided by M2 into W1. I have to find out what is M2, molar mass of solute. Now, I took M2 on the left hand side and I got an equation. M2 is equal to Kf into 1000 into W2 divided by delta TF into W1. By knowing all other terms, I can find out what is M2, molar mass of solute. I got an equation to find out how much amount of solute that I have added. Again, it's a colligative property. It depends only on the number of particles of solute, not on its nature. We have studied 3 colligative properties, and in the next video, we are going to discuss the 4th colligative property called osmotic pressure. And see you in the next video. Bye bye.